Hello and welcome back to Fourier Transform, the video series where we look at a special operator that acts on functions and is given by an integral transform. And indeed, in today's part 30, we will see that this operator has a fixed point, so a function that is not changed after applying the Fourier transform. However, before I show you how this function looks like, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Patreon or Steady, you can download the additional material for this video. And then without further ado, let's immediately fix the goal of this video. We want to show that a particular Schwarz function f defined on Rn is a fixed point of the Fourier transform. And the definition of this function is actually quite simple because it's just an exponential function. And in the exponent we find minus 1/2 and the standard norm of x squared. And when we say we have a fixed point of the Fourier transform, it just means that the output is the same as the input. And now the good thing is the key idea to show this is already given in one dimension. This means the function only has one variable and then we only find x squared in the exponential function. And to avoid some confusion, let's use the letter g in this one-dimensional case. And soon you will see the key idea here is that we consider a special ordinary differential equation. And this one is given by g prime is equal to minus x times g. So maybe at the moment this ODE seems to come a little bit out of nowhere, but I can immediately tell you the motivation. In fact, the main point here is that the Fourier transform f transforms derivatives into multiplications. More precisely, if we just write del1 for the differentiation operator given by the prime, then after pulling it out of the Fourier transform, it becomes a multiplication operator. More precisely, it's I times the multiplication operator with the identity function. So please note, this result is exactly what we have proven in the last video. The only thing you should know here is that we just consider the operators in one dimension. So if you want, instead of del1, you could also write d dx. However, I usually want to avoid that because otherwise we have a variable name involved that is not needed in the formula. We have the same thing with m1 if you apply it to function h with variable name y. Then this one would simply be given by y times h of y. And you immediately see this is really similar to our ODE from before. In fact, now let's say that the ODE holds for the given function g. Hence, instead of the derivative, we can just write the multiplication operator m1. And also there, it's possible to pull out this operator and then it becomes a differentiation operator. Indeed, this is the second formula we have discussed in part 29. It's given by minus I times the derivative of the Fourier transform of g. And now if you compare the two results, you first see that the I cancels, and then you see that we still get an ODE for the Fourier transform. And as always, let's call the Fourier transform of g, g hat of p. And now actually the derivative of this function is involved here. And by the equations from before, we just see that this one is given by minus multiplication operator of g hat. Or in short, just minus p times g hat of p. In other words, g hat satisfies exactly the same ODE as g. In fact, the only thing that changed is the name of the variable, and this one does not matter for the ODE anyway. Therefore, the next natural question should be, what are the possible solutions of this ODE? Because now we already know, if we start with one solution, then the Fourier transform maps it to another solution. Therefore, by knowing the set of solutions, we know what the Fourier transform can do. And now the good thing is that this is just a linear ODE where we have a nice method to find all solutions. And this one is the so-called method of integrating factor. And in order to start that, we have to bring everything to the left-hand side, and then we have to find an antiderivative of the factor in front of g. And this is not hard at all, it's just 1/2 x squared. And now we take this in the exponent of an exponential function and multiply it on both sides. And then we just have the two terms here in the sum multiplied by this factor. However, now by construction, we find the inner derivative in front of the exponential function. And this means we can just shorten the whole thing by using the product rule of differentiation. This is easy to check. The product rule applied to this product gives us exactly the sum above. And now you see why this method is called integrating factor, because after multiplying with a factor, we can just integrate the whole thing. And there, please don't forget, we always get an integrating constant. And in our case here, this can be any complex number. And there we have it. The solution set of this ODE is just given by multiplying this exponential function to the right hand side. And that's the reason for the minus sign in the exponential function. And by putting everything together, we actually already know the Fourier transform of this exponential function. Namely, we know the Fourier transform has to be a solution of the ODE as well. And this means that the only thing that the Fourier transform can introduce is such a constant c. And otherwise the function has to look exactly the same, so we have g hat of p is equal to c times e to the power minus 1/2 p squared. Moreover, because we have this nice formula for g hat, it should also be easy to calculate the constant c. Namely, let's put in the origin for p. Clearly, g hat of 0 gives us c. On the other hand, this one has to be given by an integral because it's a Fourier transform. And please don't forget, the factor in the front we have chosen as 1 over the square root of 2 pi. And inside the integral we have the definition of the Fourier transform, but for p we have a 0. So this is just 1, and we just have to integrate the function g. And there you might know that this integral is exactly given by the square root of 2 pi. In other words, everything cancels here and we get out exactly 1 for our constant. And this immediately tells us that the function g is actually the fixed point of the Fourier transform we searched for. However, I think before we continue, it could be good to show you the calculation for this integral explicitly. So I call it an interlude because it's not about a Fourier transform, but just about calculating a special integral. So we want to calculate this integral here, and the main trick is just to square the whole thing. Because then we can just write it as the product of two integrals where we have two variables involved. Obviously it does not matter how we call the variables, so let's go with x1 and x2. And now let's use Frobenius theorem backwards, which means we can write it as one integral over the product measure. So now we integrate over R2, and we can also bring the two exponential functions together. And this is exactly why this trick works, because now in the exponent we see that we have the standard Euclidean norm in R2. So we can just apply a change of variables for the integral and go to polar coordinates. Indeed, in R2 the polar coordinates are quite simple. We just have x1 given by r times the cosine of phi. And moreover, x2 is given by r times the sine of phi. And there the radius r goes from 0 to infinity and the angle phi from 0 to 2 pi. And now by substituting everything just means that we have r squared in the exponent of the exponential function. And please don't forget, the change of variables formula also has the Jacobian determinant involved, and for the polar coordinates this one is simply given by r. Which also means that phi is not involved at all, so the integration with respect to phi is quite simple. We just get the factor 2 pi and we only have to integrate with respect to r. And this one is not a problem anymore, because now we have the factor r in front, which is exactly the inner derivative we need to find the antiderivative. Indeed, this one is just minus the same exponential function. And now we just have to evaluate the whole thing from 0 to infinity. And since the function vanishes when we go to infinity, only 0 remains. So we only get out the factor 2 pi, which is exactly what we wanted, because now we only have to take the square root on both sides. So this calculation completely explains why our constant c from before has to be equal to 1. And with that we almost have everything, and we can formulate the important result of this video. So if we go back to the beginning where we have our n-dimensional case, we have this function f given by this exponential function. And now our nice result is that the Fourier transform f hat is given exactly by the same function. In other words, this is a fixed point of the Fourier transform. Nothing happens after applying the Fourier transform. And the only thing we have to prove now is that we can reduce it to the one-dimensional case. And you might already see it, this should be similar to applying Fubini in the calculation before. Simply because in the n-dimensional Fourier transform, we just have the inner product of p with x. This means we can just split that up into the single coordinates. And moreover, we also have the inner product x with x in the other exponential function. So I think it's helpful to make this in a concrete way, so let's split up all the exponential functions. So first we have this complex exponential function with n factors, and then we have the other one also with n factors. And then since we integrate over n variables, we can apply Fubini's theorem again. This means instead of one n-dimensional integral, we just have n one-dimensional integrals. And since these are just multiplied, we can write it with a product sign. So you see, the good thing here is that we can just combine the corresponding parts. And then the last thing we can do is to put the factor 1 over the square root of 2 pi in front of each integral. And then you should definitely see it. Here we just have the one-dimensional Fourier transform of this function. And in the one-dimensional case, we have already shown that we have a fixed point. This means this whole thing is equal to the exponential function with pj squared in the exponent. And then finally, going over the whole product gives us our n-dimensional function as expected. So there we have it. This is the special Schwarz function that stays fixed under the Fourier transform. This is a really important result because it tells us that for this example, the output of the Schwarz function is a Schwarz function again. And this is something we can try to expand to get a general result for the Schwarz space. And I can already tell you, this is what we will do in the next video. So I really hope I meet you there again and have a nice day. Bye bye.